but yeah, for this we use Haskell as our implementation language. So in this talk we are going to look at functional solutions for the longest uptrend problem. And before understanding the solutions, we have, of course, to know the problem. For those who don't know the longest uptrend problem, or better known as the longest increasing subsequence problem, here's a brief description. So given a sequence of elements, we are looking for the longest subsequence that is strictly increasing, and the subsequence is given by just removing 0 or more elements from the original data. Here you can see an example. In orange are the orange dots are the longest increasing subsequence. Actually, in general, we have to talk about a longest increasing subsequence. It's not unique in general. So this problem is a very standard problem, and we tried to come up with our own functional. So in the imperative world, it's a standard problem for program derivation, and we wanted our own implementation functionally, and we implemented it, and then we made something that one shouldn't do if one wants to avoid problems. We implemented also the imperative solution and benchmarked them against each other, and of course the imperative solution was much faster, so roughly 6 times. And so the goal for us was then to come up with a solution that is on par in real world with the imperative one, because we believe that functional programming is at least as good as imperative one, also performance-wise. So, and to understand what was our mistake first, let's have a look at the imperative standard solution. So here you can see some pseudocode, and you don't have to understand all the details. The main idea is that we have an array. Here it's called S. And in the array S, we store all the, in the array S, we store at index I the longest increasing, at the index I, we store an upsequence that has length n minus I. So you see at the end, we return Sm, and the length is n minus m. And the main logic happens inside this for loop, where we go over all elements in reverse order. And what we basically want is to extend an upsequence that we are given. So in case we can extend the longest found upsequence so far, yeah, we do this. And otherwise, we perform a binary search to find the smallest I, such that the sequence at position I is extensible. So we have here Si, that's extensible by A, and we extend it and replace Si minus 1 by the new extended sequence. So Si minus 1, the head element is smaller than A by definition. So this one has the same length, but is better because its head element is greater. So, and now what we did was to basically take this implementation and translate it directly into functional code, by basically just replacing the array with a persistent sequence type. And if you do this and choose the correct sequence type, you still get the same asymptotic performance. You see here in the for loop, the only non-constant time operation is the binary search operation, and this takes log n time, so the whole solution takes worst case n log n time. And so, and if our solution, if this sequence type supports binary search, lookup, and update in log n time, we still get a functional n log n time solution. But you see in the benchmarks, the performance is in reality much, much slower. So, and our mistake was that exactly this part here that we used integer indices to communicate. So we use integer indices to perform the search. We make a lookup, and we move also in the sequence. So here you see we have I and I minus 1. So we use integer indices for all different parts, and that's quite slow in a random access list in our case. So now we take a standard solution. We take Huet zippers instead, and instead of using integer indices, we are going to use zippers for encoding our positions, and then we have, of course, to adapt binary search to work with zippers, and in the end, we adapt the longest uptrend implementation to work with the new binary search. So here's a quick refresher on zippers. So zippers are, as I said, a functional solution for encoding locations. For example, here we focus on the location on the node 4, so we have that's our focus, and a zipper consists of a focus and of a context. In the first case, the context is empty, indicated by the T, and we can move inside the data structure. And since, I forgot to say, we are first using zippers on binary trees, and because that's what we are going to use. So, and we can go right or left, and then right and then left, and then we have here our focus is on the tree with root node 7. So we can have direct access to the 7, and the remaining part here is the context. So, and the context is basically a tree with a hole and an upwards pointer, and a location is then just a pair. So how does binary search now look like if we use zippers instead of integer indices? And so the input to binary search is really still the same. We take predicate and the tree, but instead of returning an index, we return a zipper, but not one, but 2 locations. Why this? So we return a tipping point, and if you want to know why it's in general the right thing to do to return a pair in binary search, you can attend my talk on Wednesday where I am going to talk about binary search in general. But here we can also already see why it's a good thing. You know, here, as I said, we use the position I and I minus 1 to perform a lookup and an update. So actually we, using integers, obfuscated the fact that we move inside the tree. So actually we have 2 locations, not 1, and binary search returns both locations, a tipping point, and now the binary search is implemented by a worker function, find. And let's have a look at an example where where our predicate is if 5 extends the sequence. So in our tree we store up sequences, and since we are only interested in extending them, only the heads are visible. So you can think of P if 5 is less than the element given. So we are focusing on the 4 at the root, and now 5, of course, does not extend 4. So we have in our operation find, we have the current location where we are looking at, and we have also two accumulating arguments. And since 5 does not, so for the potential left endpoint and potential right endpoint, and I forgot to mention why we are returning maybes, because the tipping point could be on the very far left or on the very far right, so we are using maybes for this. So 5 does not extend the sequence starting with 4, so we have a potential left endpoint, the negative point of the negative part of the tipping point. So, but 5 extends 9, so we have a potential right argument, and now 5 also. So we're focusing now on 7. We have a new positive endpoint and 6, and now we are in a leaf, and we return the negative and the positive part. So that's then our tipping point as expected. So how does this help now with the longest uptrend problem? So now the longest uptrend function, it starts as in the imperative solution, it starts with a singleton tree in this case containing the empty uptrend. That's always a solution, that's always an uptrend, and in the end we return the leftmost uptrend in the tree, so that's then the largest one. And now the main logic happens inside the insert operation in fold R. So we have two cases. First, first we look at the second case here, the second line. So in this case, we have two locations given, and now we have direct access to the uptrend starting with 6 in our example, and the uptrend starting with 4, and we are doing the replacement. So we take the uptrend starting with 6, add 5 in front, and put it in here, and replace it, and zip the left endpoint, so we make a tree out of it again. So that's the one case. The other case is if the tipping point is on the very far left. It can't be on the very far right because the empty up sequence is always extensible. So it can be, but it can be on the very far left. What are we doing in this case? In this case, we take the leftmost. We are then at the leftmost element, and we, for example, if our element that is our A is 0, we just take the uptrend, extend it by 0, and make it the left child. So far, so good. But unfortunately, this picture is a complete lie because we can't get into this situation. As you probably already noticed, the only part where we are extending the tree is in this second part I showed you, and it's always extending to the left. So actually what we have is a degenerate tree, and binary search is just another name for linear search. So that's not fast at all, and we get actually an n-squared algorithm. And again, fortunately, there is an off-the-shelf solution for this as well. We take Okazaki's red-black trees, and it's actually quite easy to adapt to red-black trees. So everything just stays the same. We have to add color fields to everything, and instead of zipping, we have to balance as well. So let's have a look at an example. So you can see here our input sequence, and we start, of course, with the singleton empty uptrend. So 8, of course, extends the empty uptrend, so we make it the left child, and when inserting something, we color it in red. So now 9 does not extend the uptrend starting with 8, but it extends it with the empty uptrend. So the tipping point is here in between. So instead, 9 now will replace the 8 here. So now 6 extends 9. So 6 becomes the leftmost child, and since we are having a red-black tree, we make this rebalancing operation. So again, 7. For 7, the tipping point is in between here. So we replace now the 6, the uptrend starting with 6, with the one starting with 7 that extends the one here. Now 4 again extends 7, 5 updates, 2 extends, and we have to rebalance again. Now 3 again, here's the tipping point. 0 extends, 1 replaces, and 0 in the end extends again. And so 0 extends again, and we make 2 rebalancing operations, and the tree is nicely balanced. So if you watched closely, you noticed that actually we only operated on the left spine. From the rebalancing operations I showed you earlier from the red-black trees, we only used 1, since we're operating on the left spine. So this leads us to the idea that maybe instead of using red-black trees, we use the left spine view of the red-black trees, and indeed, if we watch closely, we see that actually, if we are the shape of the red-black trees are very regular, and we are working on a numerical representation with digits 1 and 2. So if we have a black node, that's 1. So, but if we have a red node, then there must be a black node with the same height again, and here and here, and for example here in this one. So, and this is then a 2. So now instead of using red-black trees, we can actually just operate on the left spine view instead. And we actually don't need red and black nodes anymore, because we can just encode the digits inside the data structure, so as a data type. And so again, we perform the same things as before. We have again to define zippers on the left spine view, and interestingly, the left spine view is already itself a zipper. Yeah, it's actually the zipper of the leftmost leaf. So and so if we now define zippers for the left spine view, we actually have zippers of a zipper of a zipper. And yeah, again, we have then to adapt binary search, and this becomes now exponential search, because we start at the very left, yeah, and the trees are growing. So, and yeah, and in the end, we replace just the binary trees with a red-black. We replace the red-black trees by the left spine view by these finger trees. And if you want to know the details, you have to look into the paper, in particular also the correspondence between exponential search and this search in the left spine view. And so our initial problem was we wanted to have a real-world fast implementation. So did we succeed? Here are some benchmark numbers, so the same benchmark again, but now with some other implementations. So the black line here, this was the imperative solution, and this one was our initial failed attempt. Here's another standard solution from algorithm design with Haskell from Bird. And so you probably, it's fairly visible. So in dotted black, you see the imperative solution by using exponential search instead. And then in blue, you see the solution using red-black trees, and in green, the left spine view implementation. And they are all fairly close. Why are we using then, why was it worth to implement the finger trees as well? So if you remember back this example here, we only extended to the left, or the tipping point was here between the leftmost element and its neighbor. So in this case, and so if the input sequence is nearly sorted, then we only operate farther to the left. And in this case, we have adaptive behavior, and it's much, much faster, and we get actually linear running time instead. So if you want to see more benchmarks, also I also refer to the paper. So for the conclusion, it's obvious actually for us, I think, don't translate imperative code directly into functional one, but we have unfortunately fallen into this trap. And in particular, this means don't use indices blindly. Use instead zippers, use contexts. Indices are fine for array access, but they're probably not fine for accessing functional data structure. And it was at least new to us that finger trees reify exponential search as binary trees reify binary search. Thank you.
Thanks for the talk. One question I have about how to use zippers in practice for that. So if I have multiple indices, I can use them one after another to edit multiple things in my data structure. How can I do that with zippers? Because the standard way I see it, you can only have one zipper at a time.
That's true. So in maybe I should have added to the conclusion that you have to really know the problem at hand, because in our case it was really possible. But if you want contiguous indices, then I don't see how it works. Yeah.
Oh, just you also had your binary search returns two zippers. How does it work there?
So
like it returns two locations.
I showed it in the example. So we have this left argument and the right argument, and you remember this example. Mm-hmm. So we have, and we just have as our accumulators two zippers, and of course they share data, but yeah.